Last time I gave briefly the operation of a solar collector, particularly in order that we bring out the transmittance absorptance product that would be required in calculating the performance of the solar collector. Basically, the solar collector consists of an absorber with fluid passages which are pipes and then housed in a box, the bottom of which is insulated, so that the back losses are reduced, and there may be one or two glass covers, so that the convective and radiative transfer loss of heat is reduced. So, the same figure is shown here, and here is the sun, and the radiation that falls on this is I t, and something will get transmitted and absorbed over here, where tau represents the transmittance of the glass covers and alpha is the absorptance of the absorber plate. So, I have shown a typical air heater configuration also, wherein you need a large flow area, because the volumetric flow of air will be much larger for a given amount of energy gain compared to that of a liquid or water. Again, this will be a duct, and perpendicular to this the air flows and it is insulated. This is only to understand that the incoming radiation I t, for which we have made elaborate calculations, will be transmitted through the glass covers and will be absorbed, and there will be several multiple reflections between the glass cover and the absorber plate, making that tau alpha within brackets, which I shall call the effective transmittance absorptance product. Which is not exactly equal to simply the product of tau into alpha. We also have given the energy balance equation for the solar collector, which says that useful energy gain from a collector of area A c is given by the absorbed energy I t tau alpha minus the losses taking place from the plate temperature T p to the ambient T a. You may note that we represented the entire collector absorber to be at a single temperature T p, and the incoming radiation is multiplied with the effective transmittance absorptance product. We know how to calculate I t given the solar radiation on a horizontal plane. We are yet to find out how to calculate U L. T p and T a are weather data or the operating temperature of the collector. So, now our aim is to calculate this tau alpha. Also, I pointed out this I t is typically in kilojoules per meter squared hour, which is typically a short period of time that we consider. So, this U L times T p minus T a hidden multiplication factor of a time scale is involved in this. If we consider I t is 1 hour, then it will be U L into T p minus T a times 3600. This will be in joules, and if it is in kilojoules we can convert it, and that same thing has to be used consistent with the time frame that we apply. In order that the uncertainty in the plate temperature and the associated problems are alleviated, we express this useful energy gain from the collector Q u as a product of A c and f dashed times I t tau alpha, the incoming absorbed radiation, minus the losses if the entire collector had been at the local fluid temperature mean. So, instead of T p I represented T f m. So, this is an underestimate. So, to compensate that, this f dashed, the collector efficiency factor, is introduced. We shall have the definition little later. And further, again this T f m f dash is actual energy gain by the energy that would be gained if the collector is at local fluid temperature. In other words, this represents the energy that would be gained by the solar collector if the heat transfer coefficient between the fluid and the passage is infinity. To avoid this uncertainty of the mean fluid temperature, this is further refined as Q u A c, a factor f r instead of f dashed times the absorbed energy minus u L into T f at the inlet minus T a. So, T f I is a single point temperature. So, there can't be any uncertainty whether it is the average of the inlet and the outlet or the temperature at the average position, etc. So, now F r will be defined as actual energy gain if the entire collector is at fluid inlet temperature. So, this is the minimum loss that will be taking place from the collector. Consequently, this is the maximum possible energy gain. So, to compensate this underestimation of the loss, we have put the heat removal factor F r, something like effectiveness for a heat exchanger that you are aware in heat transfer studies. Now, let us examine what is happening to the incoming ray. Now, we know I t how to calculate. Now, we are set about to calculate tau alpha, that is the effective transmittance absorptance product. If this is your absorber and this is the glass plate, my incident solar ray of I t will be penetrating, and if that is a unity, this will be tau alpha into I t will be absorbed, a part of it will be reflected, which will be 1 minus alpha into tau into of course I t. Again this process keeps on happening, this will be 1 minus alpha into rho tau into I t. The reflectivity of the glass surface is rho. So, a part of it will be reflected. So, this continues, and if you sum up the total absorbed energy or the effective transmittance absorptance product the product tau alpha, this typically summation over infinite number of reflections this should be equal to tau alpha by binomial expansion 1 minus alpha times rho t. This is the diffuse or reflectivity of the surface. So, this is the actual formula for the effective transmittance absorptance product, which tells us it should be little higher than the actual tau into alpha. And as a simple thumb rule is effective transmittance absorptance product is approximately equal to 1.02 times tau into alpha. That means, it is about 2% more than the product tau and alpha. Now, if we plot the variation of transmittance absorptance product at any angle of incidence theta by the normal transmittance absorptance product, that is at theta is equal to pi by 2, this will be 1 at theta is equal to 0 and this is pi by 2, something like this, it will go to 0. This is one glass cover. If you have two glass covers, it will be slightly something like this. A simple minded calculation will be tau into alpha, which will be less than tau into alpha. Consequently, the effective transmittance absorptance product for two glass covers will be less than one glass cover. Now, this is described by Ashray Now, this reference to tau alpha n, that is the transmittance absorptance product at normal incidence, is a material property. Okay, that will be the highest for the given material or glass cover and the absorber. If the incident ray is normal, then you have the maximum transmittance, because the path it has to traverse will be minimum. This is described accurately, adequately rather, for 0 then theta less than 60 degrees equal to, and this B 0 is called the incidence angle modifier coefficient. In other words, this modifies the transmittance absorptance product from the value at normal incidence by a certain fashion. However, there was no description for theta greater than 60 degrees. We proposed at IIT Kharagpur. This can be given by for theta less than or equal to 90 less than or equal to 60. This is if you put theta is equal to 60 degrees, that will be 1/2, which will be 1 plus B 0, which is the same as the first one, and at theta is equal to pi by 2, it will be 0. So, it follows the line between 60 and 90, very close to the data values. And the typical values for B 0 are minus 0.1 for one glass cover, or minus 0.11 at times, and equal to 0.17 for 2 glass covers. So, what we have now is tau alpha at any theta can be calculated if tau alpha n is known. So, tau alpha n is a material property assumed as known. So, we know the transmittance absorptance product at normal incidence, and we can calculate at any other angle of incidence with this law, which contains the incidence angle modifier coefficient B 0, and which will take on the value of minus 0.11 or minus 0.17 depending upon 1 glass cover or 2 glass covers. Now, the absorbed radiation S is given by incident radiation multiplied by effective transmittance absorptance product. Now, we know that this I T comprises of direct radiation and sky diffuse radiation plus ground reflected radiation we can say that the direct radiation strikes the surface at the angle of incidence theta, but the sky diffuse radiation comes in all possible directions. We do not know what is the effective angle of incidence for the sky diffuse radiation. This is for direct, this is for sky diffuse. Okay. Now, for the ground reflect radiation, similarly this is also diffuse radiation. This will be effectively striking the surface at an angle of incidence of theta g. We have no idea of what is theta d and what is theta g, but for a given hour, day, location and orientation of the collector, we can calculate the angle of incidence at which the direct radiation strikes. So, to distinguish theta, theta d, theta g, I shall fill in these blanks with tau alpha designated with tau alpha b, this one with tau alpha diffuse and this one with tau alpha ground reflected radiation, right. So, now my total tau alpha is a summation of 3 components: tau alpha direct, tau alpha sky diffuse and tau alpha ground, associated with the corresponding components of the solar radiation striking the surface. So, Brandmuir and Beckman they have correlated theta g, the effective angle of incidence for the ground reflected radiation, as 90 minus 0.5788 beta plus 0.00269 beta square, where beta is in degrees. the slope of the collector. Now, we can use the terminology collector, because this tau alpha deals with the collector instead of a general tilted surface as we have been doing in calculating IT, HT, etc. Similarly, the effective angle of incidence for ground reflected diffuse radiation is given by 59.68 minus 0.1388 beta plus 0.001497 beta square. Now, if you see the ground reflected radiation theta g, if beta equal to 0, this theta g will be 90 and making the tau alpha g 0. That means, if beta is equal to 0 is a horizontal surface. So, there will be no ground reflected radiation falling and also the consequent transmittance absorptance of that radiation. Similarly, this is close to 60 degrees. If beta is 0, it will be only 59.68 and cos 60 degrees is 0.5. So, if you have a horizontal collector, our transmittance absorptance product will be corresponding to theta is equal to 60, which is cos 60 is a half. So, now we have to evaluate, bear in mind at theta a function of phi, beta, delta and gamma of the direct radiation, and this tau alpha diffuse by tau alpha normal at theta d given by the above equation, and tau alpha ground by tau alpha normal to be evaluated at theta g as given by the previous equation. Now, you have to remember one thing, the relation which we have written or this is not to be confused it is not just for the overall transmittance absorptance product, it is a property how transmittance absorptance product ratio with the transmittance absorptance product at normal incidence. The same relations yield all the ratios of direct transmittance absorption product tau alpha g upon tau alpha normal, tau alpha d upon tau alpha normal when theta A, theta B, theta G or theta D. So, you use theta B, you will get tau alpha B by tau alpha n. You will use theta G or theta G, you will get this corresponding transmittance absorptance products ratio with respect to the normal incidence value. So, it is not difficult when once, because theta D and theta G, the correlations are available which have been developed by Brian Mueller and Beckman. So, you can calculate tau alpha at any instance time of the day or the location, calculating theta D and theta G. Fortunately, they depend only on your slope of the collector beta and nothing else, and one can calculate this transmittance absorptance product effective. Now, how do we do or calculate daily or monthly average daily transmittance absorptance product? So, if I give a symbol like we had R B bar and R bar, if H T is the daily radiation falling on the collector surface, that multiplied by effective transmittance absorptance product for the day, I should be able to get it as a summation from sunrise to sunset of I T tau alpha. This should be equal to summation of the direct radiation component So, you will notice in all these summations, I am only categorically stating sunrise to sunset. Now, we know that this will be for the apparent sunrise to sunset, whereas these two components will be from physical sunrise to sunset. Nevertheless, in general we can write them as SR and SS. So, if I express like we had done it for R bar, this need not be a bar. Fortunately, tau alpha bar D, tau alpha bar G same as tau alpha D or tau alpha G for a given beta. Since it is only a function of slope of the collector, it does not change from hour to hour. So, the average daily transmittance absorptance product for the diffuse radiation or for the ground reflected radiation is a single number, which can be pulled out of my summation sign. Consequently, the summations will be H and H d over the day. However, since I b changes, this tau alpha bar for direct radiation should be defined as a weighted average this is the absorbed direct radiation by the absorbed radiation falling on the collector, which will give you the average transmittance absorptance product for the direct radiation. So, if we define a overall tau alpha bar upon, now I have divided throughout with tau alpha n for normalizing. This algebra you can do straightforward. What we have done is divided throughout with tau alpha normal to make them the ratios of tau alpha bar b by tau alpha n, tau alpha bar d by tau alpha n and tau alpha bar g by tau alpha n. Divided then again H t, which will be nothing but r bar into h. So, that and expressing H b as h minus H d like we have done earlier, you get this simplification factor. Okay. Now, this needs to be evaluated with the data as a weighted average of each hourly value. So, this I have already mentioned that tau alpha bar d and tau alpha bar g can be evaluated when once we know theta d and theta g, which are simple functions of the slope of the collector, and this needs to be a weighted average. Klein et al. Have evaluated this tau alpha bar b by tau alpha n given by sigma I b r b tau alpha b upon tau alpha n, again sunrise to sunset appropriate by I b r b sunrise to sunset. What are the approaches that are available? Use data. So, you have a large database like TMI2, but covers about 25 degrees latitude to 49-50 degrees latitude, or it may not be covering all the lower latitudes. That is one part. The second thing is one may not be able to have values for a regular variation of phi, particularly beta, delta and gamma are in my hands, but not latitude. Okay. So, the other alternative is RT and RD correlations can be used, right, where you have got RT is pi by 24 a plus b cos omega times cos omega minus cos omega s by sin omega s minus omega s sin cos omega s. You can check this relation. Similarly, R d is pi by 24 times cos omega minus cos omega s by sin omega s minus omega s cos omega s. So, I b, as we had done earlier, I minus I d R t into h minus R d into h d, or one might write it h times R t minus R d by R t times the diffuse fraction h d by h. Okay. So, now from this relation, this is our standard symbol which we have been using as df, the diffuse fraction. So, I can expect in general tau alpha bar b upon tau alpha normal a function of phi, of course, beta, delta, gamma and n g. This what I will call it the number of glass covers. This is in general what I would expect, and in addition the diffuse fraction. So, having got this tau alpha bar b by tau alpha n number, whether it is calculated using the data or whether it is calculating RT and RD correlations, they have put back in the relation for tau alpha by tau alpha normal and found theta b, because it is a day. This is the theta b bar, the so called effective angle of incidence for direct radiation. Okay. So, if you have got this, and now as I claimed, this should in general be a function of phi, beta, delta, gamma, df and ng. So, they have been given plots were given as a function of phi, beta, delta, and gamma only. The dependence on the climate or the diffuse fraction or the number of glass covers is not available in those plots. So, they typically look something like this. This is with respect to beta and theta b bar. This is for latitude of, let us say, 30 degrees, and you may have this is for December, this is for June. So, in between November etcetera, depending upon the decreasing order of magnitude of declination, they will be appearing, and this is for gamma equal to 0. So, you have several plots for phi is equal to 20, 30, 40, 50 and perhaps 60 and 70 also. Similarly, gamma is equal to 0, 15, so on and so forth, and the beta 0 to 90 degrees. So, this tau alpha bar b by tau alpha n not being dependent one possibility is dependence on N g may be small. Reason: tau alpha changes, tau alpha normal also changes. So, tau alpha by tau alpha normal in general average may be independent of N g, but dependence on d f needs to be investigated. So, you may recall R b bar t a function of d f and varies by 10 to 15% compared to R b bar under extraterrestrial conditions. So, can we not expect to be similar? So, what we try to do in this lecture is essentially we have given the useful energy gain equation for a solar collector, particularly a flat plate solar collector. In that we know how to process the incoming radiation. Then we identify that there is a optical property, transmittance absorptance product, comprises of 3 components for the direct radiation and for the diffuse radiation and the ground reflected radiation. This tau alpha d and tau alpha g occur at effectively at theta d and theta g, correlated by Brand-Muir and Beckman. Klein produced graphical results for theta b bar the effective angle of incidence for direct radiation, as a function of latitude of the location, slope of the collector, the month and the azimuthal angle. But in general, theta b bar can be expected to be a function of phi beta delta gamma, diffuse fraction and the number of glass covers. This needs to be examined.